Hello, my name is Gunwant and I am from group 316. So here my topic is the physics of the membrane in which the conformational properties of the membranes. Now let's get started. Membranes are the dynamic structure that combine high ordering with the fluidity and the lability, enabling them to perform their essential functions. The liquid crystalline properties of biological membrane are determined by the lipid present in them being, being in a molten state at physiological temperature. The melting temperature of hydrocarbon is lower, resulting in large double bond which give rise to a difference between animal fat and vegetable oils. The liquid properties of membrane can be revealed through various methods such as magnetic and fluorescent levels, NMR method, and EPR spectrum analysis. Photoreceptor membrane containing the protein rhodopsin have been extensively studied for their liquid crystalline properties. The the flash photometric technique has shown that the rhodopsin molecule rotate rapidly about axis perpendicular to the membrane plane with a diffusion coefficient of 3.1 to 1.5 into 10 to the power 9 centimeter. This corresponds to the viscosity from 0.1 to 0.4. Membrane structure shown masses of globular protein floating in the oil layer of lipid embedded on both sides to varying degrees in double bilayer of mobile hydrocarbon tails of the lipids. Protein span the entire membrane thickness with a considerable part of membrane surface free from protein channel in membranes. Transport small ions and molecules likely formed in the uh, vicinity of protein molecule coated with the polar groups. This is a diagram. Here first is represent the low temperature and second one for the high temperature. This diagram shows the EPR spectra of the spin level liquid molecule in the membrane. The conformational mm, transition in membranes can be detected using fluorescent and magnetic levels, diffraction and light scattering and circular dichroism. The phase transition, such as melting of lipids, occur near 0 degrees Celsius when the mitochondria and the microsome uh, are heated from the minus 40 degrees Celsius. Spin level in membrane can also help in understanding the nature of these channels. The lipid membrane of mitochondria and microsome undergo a transition near 0 degrees Celsius when heated from minus 40 degrees Celsius. The lateral phase separation in liquid is determined by their conformational properties, with the melting of lipids occurring through rotational isomerization of hydrocarbon chain. This results in the crystallization of saturated carbohydrate hydrocarbon, this is called paraffins, in form of continuous series of rotamers, which also give rise to a Gauge rotamers. These fraction in liquid paraffins hydrocarbon is about 10%. The heat capacity and the enthalpy of solution of lipid diplomatic nesting change with the temperature with two-phase transitions observed at 34 degrees Celsius and a sharp one at 41 degrees Celsius. The statistical mechanics of bilayer phospholipid membrane considered rotamerization and interchain steric restriction and the enthalpy and the entropy changes brought about by the melting of a bimolecular lipid layer are formed to be an agreement with the experiment. The Treble in 1977 also advanced the theory of transport of molecule across the lipid membrane based on the rotamerization of hydrocarbon chain. Strigate rotamers are more mobile structural defects that determine the presence of free volumes in hydrocarbon phase of the membrane. So here's the diagram of the temperature dependence of enthalpy and the heat capacity of the solution of dielectric and lattice. So here the conformational changes are uh, might crucial in the interactions of membrane with the ligands, which is essential for physiology and pharmacology. The response of cell membrane to specific ligands is typically cooperative with curves displaying infections. For example, cholinergic strains of bacteria produce macromolecules antibiotics which can destroy sensitive strains of E. coli. The membrane of a sensitive cells has amplifying properties with the reception of one molecule serving as a trigger for macroscopic event on the cell scale. Many drugs have been an effect on membrane mm, conformations and membrane lipids. Now, the Changius and the Changwix and his colleagues treated the cell membrane as an ordered cooperative system of interacting summits considering the triggering properties of membrane. Each summit has a receptor site for a specific ligand and the affinity of which is changed when its conformation is altered. The response of the membrane to ligands additionally may be gradual or sigmoidal, becoming an all or none transition. The main difficulty in building a molecular theory of membrane transport and reception is analyzing the dynamic interaction between the proteins and lipids. Membrane receptors change their conformation when bound to the ligands, leading to a change in the depth of immersion and mobility of protein in the lipid sea. The fluid mosaic model may serve as the basic for the molecular physics of membrane. Now, it's complete. Thank you.